Okay, so assumption. So we are going to make one assumption before we handle the random H part. So the assumption is that our hypothesis class is finite, right? I'll talk about this in a minute. Finite hypothesis class. What does this mean? This means that we have our data, and the data from the data we want to learn some classifier, and that classifier comes from a hypothesis class. So if I say it's a linear classifier, then W is what we are learning, and then W is just a d-dimensional vector, and then there are infinite such W's. So that's an infinite hypothesis class. But now for a simple assumption, and then we'll talk about infinite assumption hypothesis class later. For now, let's say I only have a bunch of possibilities, H1, H2, H3 till Hk. Let's say I have only k is let's say 20. I have only 20 classifiers. Given your training data, I want to pick which of one of these 20 classifiers. That's the only thing that my algorithm is going to do. It's not going to look at infinite classifiers. It's not going to do an optimization or anything of that sort. It can do optimization, that's up to the algorithm, but it's not going to deal with an infinite hypothesis class. Let's say my bag from which I'm picking a classifier does not have infinite possibilities. It has only finite possibilities. That's a finite hypothesis class case, right? Now, we'll see why this is a useful thing, and then of course this is not practical, right? So let me tell you right away that this is not going to be practical, because we are never going to search in a finite hypothesis class. All the machine learning algorithms that we have seen has some parameter that it is optimizing, and that parameter comes from an infinite, has infinite possibilities. It might come from RD, right? So if you are learning a W, you are not only allowing finite set of W's, you are allowing any W to be possible, right? So this is not what machine learning algorithms do, but if you don't answer a simpler question where you only have a finite bunch of things to choose from, if you cannot answer the question of whether my train error is a good proxy for the test error, then it's going to be much harder when you're actually working with machine learning algorithms. So we'll start here and then we'll go there. Okay, so I want to define two events. Event A is the problematic event that my train error and test error of the learnt classifier are far away. What is this? Let's look at this carefully. So here is an event. So I'm calling this event because my S is random, and then I'm learning, my learning algorithm picks, using whatever the algorithm is, picks one of these H1 to Hk, and then let's call that Hs because the S gave that, and that's the training error of RS of Hs is the training error, RD of Hs is the test error of the random Hs, and the event is that this difference is greater than epsilon. Event B is that maximum difference between the train and the test error of any classifier in my hypothesis class, which is, remember, a finite hypothesis class, is greater than or equal to epsilon. Now, what does this mean? This means that I look at the difference between the train and the test error of each of the H in my bag, right? So the data set came, it was random. Now I have a hypothesis class, and now I can ask, I'm not even running any algorithm for this to compute this B, right? So I'm asking, I'm taking every H1, computing the train error, test error, and computing that value, taking H2, computing the train error, test error, and doing that for each of my finite number of hypotheses that I have in my bag, and I'm asking, and the event is that the maximum among these differences, the generalization error of H1 to Hk, is greater than or equal to epsilon. These are two events. Now, question for you to pause and think is, does A imply B or does B imply A? in other words, if A implies B, then it means that if the learnt classifier has a difference greater than epsilon, then the maximum difference is greater than epsilon. If B implies A, then if the maximum difference is greater than epsilon, then the learnt classifier's difference is greater than epsilon. Which one do you think is correct? Well, it's not too hard to see. Pause and think about that. The answer is, A implies B. Why? Because, here is H1 to Hk. So, maybe my learnt classifier was H2. And for H2, the difference was greater than epsilon, right? So, if the difference, which means that if event A happens, then that means that the learnt classifier, which in this case is H2, had the train and the test error with a large difference. Now, if the learnt classifier has this, then the maximum difference will also be greater than or equal to epsilon, because H2 itself has greater than or equal to epsilon. So, even if the others do not have, for all the other classifiers in my bag, if the train and the test error were close to epsilon, still H2 has it greater than or equal to epsilon. So, A implies B. Now, if A implies B, if event A implies B, then we know that probability of event A is at most the probability of event B, right. So, in Venn diagrams, if this is A and this is B occurring, if A occurs, then obviously B also occurs. So, the chance of A occurring is bounded by the chance of B occurring. So, then what does that mean? That means that the probability of the difference between the train and the test of the learnt classifier being greater than epsilon is at most the probability of the maximum difference between the train and the test error of any classifier in my bag. Now, why are we doing this? So, the biggest problem that we faced earlier was this was a random quantity and this was also a random quantity. Now, what we have done is, it's hard to analyze the difference between these two random quantities and then asking if that is greater than or equal to epsilon. But now what we have done is, we are saying I do not know the exact probabilities, but I am saying it is at most some other probability which involves two terms, where of course there is a random term, but then this guy is non-random. There is no S dependence on the second term, and we know how to handle this, right. So, Hofting would help us. Of course, there is a maximum here, we have to worry about that, but otherwise we know how to handle this term. So, now the problem of two terms being random has completely gone away. Now, the only thing we have to deal with is the maximum part. So, now what does that maximum actually mean? Let's talk about that maximum a little bit more carefully. So, to understand this visually, right. So, let us say this is the space of all data sets, right. So, let us call this the space of all data sets. What does that mean? That means that a point here corresponds to a data set with n data points, x1, y1 till xn, yn. Now, a point here, every point here is a data set, and there are infinite such data sets, of course. Right? So, I am just putting points here, but then this is an infinite space. Now, what is for a fixed hypothesis H, let us say H1, that is some classifier in my bag, hypothesis in my bag, there are some data sets for which H1's training error and H1's test error might be greater than or equal to epsilon. Not for all data sets, there are going to be some data sets, right. So, not necessarily for all data sets. So, let's say that set of data sets is here, right. So, this is the set of all samples, set of all data sets for which H1 is bad. When I say bad, it means that RS of H1 minus RD of H1 is greater than or equal to epsilon, right. So, that is RS of H1 minus RD of H1 is greater than or equal to epsilon, right. So, that S, right. So, S comes from this set, let us say. Now, for H2 it might be a different set. This might be H2's set, right. So, this is, let us say, H2. I am just indicating it by the color here. H3 might be something else here, and then we have till Hk, and then you have Hk, maybe Hk is here, right. Now, what we are asking is the probability that the maximum among all H, the difference between train and the test error is greater than or equal to epsilon. That is what we are asking, right. So what, how can we think of that, right. So, if any of these data sets happen, right. So, when I sample, if this data set comes, then this data set should contribute to my probability, because for this data set H1 is bad. What does H1 bad means? Well, H1 is bad means H1's train and the test error is greater than or equal to epsilon. So, the maximum will also be greater than or equal to epsilon, because for H1 itself it is greater than or equal to epsilon. So, any of these data sets, if they occur, then that is a problem, because there is at least one of these hypotheses for which the train and the test error is greater than or equal to epsilon. So, maximum will also be greater than or equal to epsilon. So, for example, if here is a nice data set, this data set is a nice data set. If this data set appears, then for all my H1 to Hk, the train error and the test error are less than or equal to epsilon. It is not a bad data set for any of these hypotheses. But if any of these orange circled ones appear, then that should contribute to this probability. Well, which means that the set of data sets that I care about is those data sets for which there is at least one H for which this data set is bad. For example, if there is a data set here, which maybe there is a data set here. Now, this is also an orange data set. It is bad not just for H1 but for H2 also, it is in the intersection, right. So, but that also has to be counted, right. So, which means this is just saying, in other words, probability that there is some H in my hypothesis class such that error S of H minus RD of H is greater than or equal to epsilon. Even if there is one H, then that data set contributes to my probability, the bad event, right. Now, when there exists H, right. So, now what I am saying is it is very hard, because these circles can intersect arbitrarily. So, I am going to kind of not worry about that intersection probabilities, and then I am going to say that, well, I will take each of these circles probability separately and then add them up. That is the union bound, right. So, this is at most the sum over all H in H. Now, the probability that Rs of H minus Rd of H is greater than or equal to epsilon, which means that, you know, I might potentially double count, right. So, this data set appears for both H1 and H2, so that gets double counted. That is why there is a less than or equal to here. That is the union bound. This is the union bound. But then something interesting has happened. The max, which is just that there exists H belongs to H, you know, in a different avatar is the max, but then that has gone out into the sum outside, right. So, but now this, for any fixed H, we already know using Hoeffding's, this is something that we can control, and we know in fact that this is exactly, you know, not exactly. So, this is at most H in H e to the minus 2n epsilon squared, and that comes just by Hoeffding's. So, this whole quantity then is just the cardinality of H times e to the minus 2n epsilon squared, because this is a sum over all H, and now here is where we have used finite hypothesis class. Right. So, if it was an infinite hypothesis class, I cannot put a cardinality there, right. So, I need a finite hypothesis class for this argument, right. So now what we have essentially then said is, remember we started with what we wanted, which is the difference between train and test error of the learned classifier from a finite hypothesis class, and then we are essentially saying, this is what we started with, the probability that RS, let me write this carefully, RS of HS minus RD of HS greater than or equal to epsilon now is less than or equal to absolute value of the cardinality of H times e to the minus 2n epsilon squared. Now we want this value to be something like delta. Remember, the dependence on n has come already, and now if I want this value, the probability of a bad event happening to be not so much, a bad event meaning the train and the test error being greater than epsilon to be not so much. If I give you an epsilon, so then I can say that this implies we want cardinality of H into e to the minus 2n epsilon squared to look like delta, which means that e to the minus 2n epsilon squared, well, we can say this at most also, that is also fine. So this is less than delta by cardinality of H. If I take log on both sides, then that is log of delta by cardinality of H. If I take a negative on both sides, and then I say this becomes n greater than 1 by 2 epsilon squared, the negative will make the numerator and denominator flip. So this would be cardinality of H by delta. So what this is essentially saying then is the following, right? So what have we proved, right? So we have proved something very, very important. If you have a hypothesis class with finite set of hypotheses, there are only 100 classifiers, 1000 classifiers, whatever this number is, right? So then what we are saying is that if my algorithm is picking a hypothesis from a finite hypothesis class, then if you give me enough samples, which is at least 1 by 2 epsilon squared log of cardinality of H by delta, then my train error and test error of the learned classifier will be within epsilon with very high probability, with probability at least 1 minus delta, or the bad event will happen with probability less than delta. Equivalently, the good event, that is it is being within epsilon, will happen with probability at least 1 minus delta. So if example, so if epsilon is 0.1, delta is 0.1, then this is saying, and if I have cardinality of H is, let us say 100 or 1000 classifiers from which I am picking, so then this is essentially saying I want n to be greater than 1 by 2 into 1 by 100 times log of 1000 by 0.1. So this would be just 50 times log of 10 to the 4. Well, if I think of this as log base 10, so then this is like n is greater than, well, log base e actually, but something like 200, right? So 200 log e to the 10, so that will be something like 3. So this is like n greater than or equal to roughly 600 to 700, right? So basically what this is saying is, if I have a hypothesis class with 1000 classifiers, I can do any algorithm. Remember, we have kind of not resorted to a specific algorithm at all. What we are saying is that whatever your algorithm be, the algorithm is going to pick one of these 1000. Now what we are saying is that I don't know which is this exact thing that your algorithm will pick. That's the problem, because the data is random, your algorithm can be deterministic, but still what it will pick is random. But what I have managed to do is, I am saying if you give me enough data, each of these 1000 hypotheses, their training error and test error will be close to each other with high probability. And so I can use an union bound to say that no matter what hypothesis your algorithm picks from these 1000, it will also be close to its train error will be close to test error, right? So because we don't know which one the algorithm exactly picks, we kind of tackled the whole hypothesis class together, right? So, and this kind of a result is what is called as, uniform convergence. A funny analogy that I think about, is the story of the Hanuman in Ramayana, right? So, I mean, if you know the story, so where Hanuman is tasked to find the Sanjeevani, herb, but he doesn't. A specific herb in the Sanjeevani mountain, but he doesn't know which one it is. So he picks the entire mountain and brings it, right? So this is exactly what we have done here. We don't know the exact HS that the algorithm will output, and we cannot, because we don't know that, it's hard to prove convergence for that specific HS. Instead, we are saying I'll prove convergence for all the H in my hypothesis class, and so it will also work for the HS that the algorithm picks. Doesn't matter which HS the algorithm picks. So now at this point, to conclude, we started by saying we wanted to compute the difference between the training error of the learned classifier and the base error, and then we broke it down into generalization plus estimation plus approximation, and now we are focusing on the generalization error. And now all we have managed to do is, if I am searching in a finite hypothesis class, then the generalization error can be for sure controlled if you have enough samples. We exactly argued what the sample complexity is. But all machine learning algorithms we know don't work in finite hypothesis classes. So to make this any useful, we have to work with infinite hypothesis classes, like linear hypothesis class or quadratic hypothesis class. And we will look at that as well next, and that's a much more interesting argument, and that will lead us to a very fundamental quantity in machine learning, a combinatorial quantity in machine learning, and we'll see that when we meet next time. Thank you.